Good morning, Kasturians. Today we are going to study the final topic of our chapter, Force and Laws of Motion, and that is momentum and conservation of momentum and third law of motion. So, what is momentum? Momentum is defined as a product of mass and velocity, and it is denoted by a symbol P. P is equals to m into v, where m is the mass of the body and v is the velocity of the body. The SI unit of momentum is kilograms meters per second. Now, what is change in momentum? The change in momentum is defined as the final momentum minus the initial momentum, where the initial momentum of the body is u and the final momentum of the body is v. Now we came across rate of change of momentum. As we know, wherever rate is asked, that means it is talking with respect to the time. So the rate of change of momentum will be none other than change of momentum upon t, which is equal to mass into mass into final velocity minus mass into initial velocity upon time. We can take mass in common and we can write final velocity minus initial velocity upon time t. This is rate of change of momentum. Now we came across conservation of momentum. So before studying conservation of momentum, we have to study the concept of system. What is a system? You can take an example like there's a moving car. So the force which is present inside the car, all the internal force will be defined as the system, while all the forces acting on the car by the environment are termed as external forces. The external forces will be like friction. The friction force which is applied by the road on the tires of the car. So if we talk about conservation of momentum, like momentum is conserved. So in an isolated system, the total momentum of an isolated system is conserved, where the isolated system in above example is car. If we take another example of isolated system, we can take two balls and we will be dealing with the derivation in this. In an isolated system, net external force on the system is zero. Let's take an example of collision of two balls. If we are having two balls, like ball A and another ball B, and we collide both of them, you can see here we have two balls, one ball A and another ball B. The ball A is having mass m1 while the ball B is having mass m2. The initial velocity of ball A is u1 while the initial velocity of ball B is u2. Both balls are moving, and suddenly the initial velocity of A, which was actually more than the initial velocity of u, due to which both the balls collide. F1 is the force applied by the ball A on ball B, and F2 is the force applied by ball B on ball A due to the collision. And afterwards, the collision, they start moving again and finally stop with a final velocity of v1 and v2. v2 for ball B and v1 for ball A. So here the total total momentum before collision of ball A and B will be defined as mass of ball A into initial velocity of ball A plus mass of ball B multiplied by initial velocity of ball B. And in collision, as we have studied in class, the third law of motion, let me tell you again. According to third law of motion, Newton stated that for every action there is an equal opposite reaction. Similar thing is seen in the earlier example of the two ball collision. The ball A provides a force of F1 towards the ball B, while the ball B provides F2 force towards the ball A. This is a perfect example of third law of motion, which is the action and reaction forces are equal and opposite acting on different bodies. You can see here in collision there is an equal and opposite forces. F1 is equal to the opposite of F2 force. Due to the opposite, we have written negative sign over here. So the total momentum after collision will be written as the mass of ball A into final velocity of ball A plus mass of ball B multiplied by final velocity of ball B. We have studied from second law of motion that F is equals to mass into acceleration. As from third law of motion, F1, which is the force exerted on B by A, is equal to the negative of force 2, which is the force exerted by ball B. So here A exerts force on ball B, which is equal to the mass of ball B into acceleration of ball B, because force is equals to mass into acceleration. Similarly, we can write here for the force of A ball, which will be written in negative. If we write down the value of A, which we have studied in earlier chapter, this A is equals to final velocity minus initial velocity upon time t. Similar thing we have done over here. So the t is common here, so it gets cut down, and we have multiplied m2 with v2 and u2. So we get m2, which is the mass of ball B, into final velocity of ball B minus mass of ball B into initial velocity of ball B. Similar thing we get here for A. Negative sign due to the opposite force, mass of ball A into final velocity of ball A plus mass of ball A into initial velocity of ball A. If we take the final values together, so mass of ball, the negative sign will turn here to the positive one. So we get the mass of ball B into final velocity of ball B plus mass of ball A into final velocity of ball A is equal to the mass of ball A into initial velocity of ball A plus mass of ball B into initial velocity of ball B. So as we seen earlier, this is the total momentum after collision, because here the velocity is final of both A and B, and this is the total momentum before collision. And both of them are equal to each other, hence the momentum is conserved. So this is all for the conservation of momentum, which states that the total momentum before collision is always equal to the total momentum after collision. We have few examples related to the conservation of momentum and in which third law of motion applies, and one of them is according to the book is when a gun is fired, the bullet moves forward, which is the action, and the gun recoils in the backward direction, due to which we get a jerk on our shoulder. This is the reaction. So action is equal to the reaction. That's all for today. Thank you.